An aircraft's total drag can be defined as the sum of its parasite drag and induced drag. This lesson examines the essential aspects and significance of total drag. If the curves for parasite drag and induced drag are plotted together, you can easily see the predominance of induced drag at low speed and of parasite drag at high speed. If the two sets of values are combined, we get a curve for total drag, a shape with which you will become very familiar. Because of the way that the two component types of drag vary with speed, the speed at which total drag is at its minimum occurs where the induced and parasite drags are equal. This minimum drag speed, usually referred to as min drag speed or VMD, is an important reference for many aspects of aircraft performance. Range, endurance, glide, maneuver, landing and takeoff performance are all based on some relationship involving the aeroplane total drag curve. Since flying at VMD incurs the least total drag for flight with lift equaling weight, the aircraft will also be at the angle of attack for the maximum lift-drag ratio, LD max, which is around 4 degrees. It is important that you remember that LD max is obtained at a specific angle of attack, and also that the maximum lift-drag ratio is a measure of aerodynamic efficiency. On this subject, it is worth noting that if an aircraft is operated at the LD max angle of attack, drag will be at a minimum while generating the required lift. Any angle lower or higher than that increases the drag for a given lift force. More drag requires more thrust, which is inefficient and costly. You should also note that if IAS is varied, the lift-drag ratio will vary. Lift-drag ratio can be presented in a polar diagram, which plots CL against CD. This shows the CL increasing initially more rapidly than CD, but ultimately CD increases more quickly. LD max can be found from the drag polar by drawing a tangent to the curve from the origin, the slope of the tangent determining the value of the maximum lift-drag ratio. This is a common method of displaying the lift-drag ratio, and you will become quite familiar with it. As fuel is consumed, gross weight reduces, requiring less lift and reducing induced drag. The effect on total drag is that the curve moves down and to the left, as total drag and VMD are reduced. If the aircraft is operated at a higher weight, the curve moves up and to the right, as a result of the greater induced drag, and VMD occurs at a higher IAS. Changes in configuration, as for example on the approach to land, where landing gear, flaps, and air brakes or spoilers will be extended in a sequence appropriate to type, will create significant increases in parasite drag, but differing variations in induced drag. More lift with flaps with the increased CL, less with spoilers. The overall result is an increase in total drag, but a reduction in the min drag speed, with the curve moving up and to the left. Since transport aircraft tend to operate mostly at steady indicated airspeeds, it is relevant to consider variations of drag with IAS. At a constant IAS, dynamic pressure remains constant, so even if altitude is changed, drag will not change, even though TAS will change according to the changes in density with climb or descent. For an aircraft to be in steady flight, it must be in equilibrium. That is, with no out-of-balance forces or moments. When it is trimmed to fly at a steady speed, thrust and drag are equal. Therefore, when an aircraft is in steady flight, it can be said that the terms drag and thrust required are essentially interchangeable, so that when considering a total drag curve, it could also be looked at as a thrust required curve. For an aircraft in steady flight, if there is a change in speed without a change in power or thrust, the thrust available, there will be either an excess or a deficiency of thrust available, depending on the trim speed. We shall consider an aircraft at two speeds, at points A and B. If at speed A the speed is disturbed and rises, drag also rises, and a thrust deficiency exists. The aircraft then decelerates and settles back at its original speed. In this area of the curve, then, the aircraft is speed stable. Similarly, if the aircraft were to lose speed, drag would decrease, and the aircraft would regain the lost speed. Considering the aircraft at speed B, if it gains speed, drag decreases, and with an excess of thrust, the aircraft's speed will continue to drift up to VMD. In this area of the curve, the aircraft is speed unstable. Possibly, the most potentially hazardous situation occurs with a speed decrease in the speed unstable part of the curve, as the aircraft would then tend to decelerate further unless the deceleration is rectified with a prompt and generous application of thrust. Flight in this region of the curve is often referred to as being on the wrong side of the drag curve. Thinking back to earlier in the lesson, you will remember that lowering gear and flap and extending speed brakes lowers VMD, which has the benefit of extending the speed stable region to the left. Indeed, some aircraft fitted with air brakes routinely fly approaches with brakes out for that very reason. Finally, you will notice that the curve either side of VMD is fairly flat. In this region, the neutral IAS area, there is no distinct tendency to either speed stability or instability. However, the general rule to remember is that above VMD, the aircraft will be speed stable, and below it, speed unstable.